Hello, dear students, welcome to this video. Now we discuss the properties of carboxylic acid derivatives. In the physical property, only one point about the boiling point of acid derivatives. It is difficult to compare the boiling point of various acid derivatives like acid amide, ester, acid halide and hydride because they vary much in the molecular mass. If you consider one particular derivative like say for example acid chloride and take various homologues with increasing number of carbon, naturally boiling point will increase gradually with increasing molecular mass. But comparing the boiling point of various derivatives is not very meaningful. However, for a comparable molecular mass, we can see that acid amides are having much higher boiling point compared to other derivatives. Can you say why? It's very clear looking at the structure. You can understand here the boiling point is much higher because of greater extent of hydrogen bonding possible. Because there are two hydrogens on nitrogen, it can form intermolecular hydrogen bonding more. See, the CO also can participate in hydrogen bonding and hydrogen bond acceptor. And this is more. That is not possible in ester or anhydride or acid chlorides where there is no hydrogen, there is no polar hydrogen. In the case of the parent acid, there is OH, we have already discussed this point. It is able to have hydrogen bonding but not as much as in the case of amide. Okay. Now coming to the chemical properties or chemical reactions, that is the main focus of this class. Chemical reactions of acid derivatives. The most common reactions of acid derivatives are nucleophilic acyl substitution. This is the acyl group. Z can be OH, that means the parent acid. If it is Cl, it is acid chloride. OR means ester. This is anhydride and amide. What happens? A strong nucleophile is attacking this acyl carbon. Why? Because this oxygen is highly polar and this pi bond easily shift to this oxygen, making this carbon positive or susceptible for a nucleophilic attack. So nucleophile will attack with this lone pair of this carbon. In turn, this Z will leave. That is what is substitution. Okay, so nucleophile substitute this Z and Z become a leaving group and you get the product. So this is the nucleophilic acyl substitution. Interestingly, much of the chemistry of acid derivatives are converting one into the other. One derivative into another or to the parent acid. You will see that while discussing the reactions. In this class we discuss mainly the reactions of acid chloride because it is the most reactive acid derivative and the other derivatives will be discussed in the next video. Now we look at various aspects of this reaction. Number one, the reactivity, the origin of reactivity. See, acid derivatives are found to be more reactive towards nucleophilic substitution than alkyl halides. That's a valid point. Alkyl halides, you might have learned about SN1, SN2 mechanism. Let's take for example a simple primary halide, alkyl halide. And here some nucleophile can attack this carbon and displace this halogen. the tendency is more here. Why? The reason is this. This carbon is sp3 tetrahedral. So the nucleophile which is coming to attack this carbon has to face some steric crowding, correct? And that is not here. This carbon is sp2, correct? It is planar, flat. Nucleophile can very conveniently come without any steric obstruction either from the top or from the bottom to this carbonyl carbon. So it's very easy to attack. That's the main reason why this is more reactive. And again, the intermediate formed in the mechanism, we will see that is going to be a tetrahedral intermediate which is stable without any steric effect. Whereas here, at times, it has to form a pentavalent intermediate, and that is not sterically favorable. Okay, coming to the mechanism now. Mechanism of this reaction, it takes place in two steps. Step 1 is obviously attack of the nucleophile. Attack of the nucleophile plus nucleophile giving the intermediate. So this nucleophile is attacked this carbon and this pi electron shift towards oxygen. You get the intermediate like this, minus, okay. This is the intermediate. See that it is an sp3 carbon now. sp2 becoming sp3. So it's a tetrahedral intermediate. Now, so this is step 1. In the second step, what to happen? It's very clear. You can say, what is the next step to be? Nucleophile came and what has to go? The leaving group has to go. So it is Z is left aided by this shift of electron and this is lost. You get the product now plus, sorry, here it is, nucleophile remain here and Z minus is the leaving group. This is the mechanism. This is the second step. So attack by the nucleophile is step 1, forming the tetrahedral intermediate, and loss of the leaving group is the second step, giving the product. That's the mechanism. Now, the next point is about the order of reactivity. How do we compare the reactivity of various acid derivatives towards this nucleophilic substitution reaction? It's very, very important point. You can see the order here. Least reactivity is found to be amide for this reaction. Increases to the parent acid and ester have comparable reactivity. Increases to anhydride, and most reactive is acid chloride. That is why in the previous class we have discussed that in many reactions of carboxylic acids, it is not the acid which we start with. We convert acid into acid chloride and then go for reaction to get better products, because this is very reactive. Okay, and when we discuss the chemistry of acid derivatives, you can see that acid chlorides are showing more reactions and amides are showing least reactions. How do we explain this reactivity? It's very easy, interesting. See, look at this reaction again. See, the nucleophile is a base 2. It's a strong base because it has a lone pair, donating lone pair to form the bond. So it is a base. Actually, it is a strong base displacing a weak base. So leaving group is a weak base. Make this point clear. Nucleophile is a strong base and leaving group is a weak base. So for the reaction to be quicker, leaving group has to be weaker base. So this is to be underlined. You make this point. This is another generalization in organic chemistry. Weaker the base, better the leaving group. Underline that. Weaker the base, better the leaving group. So to compare the reactivity, what you have to do is, you consider the leaving group tendency of these groups in terms of their basicity. We can do that. Let's consider various acid derivatives and compare the reactivity. See, from this intermediate, there are two options. Either nucleophile can leave or Z can leave. It is Z which is leaving because it is a better leaving group, and it is because it is a weaker base. Okay, so weaker the base, better the leaving group. We can note the acid derivatives now here. Starting with, let me write amide first, for example. Then I am writing the parent acid also. Then it is ester, COR. This is anhydride, and finally acid chloride. Okay. Now, what are the leaving groups? If this is lost, it is NH2 minus, OH minus from acid, OR minus, OCOR minus, and Cl minus. These are the leaving groups. Now, in this, so to compare the leaving tendency, I repeat the point, the reactivity order is based on the leaving tendency of the leaving group. Whichever is better leaving group, the corresponding derivative will be more reactive. So here this is most reactive because Cl minus is the best leaving group among these three. So the leaving group tendency is increasing in this way. How do you justify? As I said earlier, the leaving group tendency depends on the basicity. What is the rule? Weaker the base, better the leaving group. So basicity decreases in this order and leaving group tendency increases in this order. Then why basicity decreases in this order? How do you understand that? For that, you can consider the corresponding acids. These are bases, okay? Consider their conjugate acids. Let me write it here. This is HCl, correct? Conjugate acid, you just add H plus to this, you get the conjugate acid. This is RCOOH, you get ROH, here you get H2O, and here you get NH3. Okay, by adding H plus you get the conjugate acid. Now, you know, this is a base and this is a very strong acid. Acidity increases, correct? This is a very strong acid, you know, this is alcohol, this is carboxylic acid. Acidity is increasing, correct? And this is weaker acids or stronger bases. So acidity increases from this to this. And again, in chemical equilibrium, you might have learned another important generalization coming from Bronsted-Lowry theory. What is that? Stronger the acid, weaker the conjugate base. You remember that? Stronger the acid, weaker the base. So HCl is a very strong mineral acid. So the conjugate base Cl minus is weak. So this is strongest acid. So this is the weakest base. This is the weakest acid. It's a base actually. So it's the weakest acid. Naturally, this is the strongest base. You might have learned about the bases like NaOH is a very strong base. NH2 is still stronger base, which we use for, you know, elimination reactions. So the point is this: basicity is decreasing in this order. Basicity decreases. Sorry, not this. Basicity of these bases decreases, or the leaving group tendency increases. So the reason is leaving group tendency of these groups is increasing. So that is the main point we have to highlight here. So we can note the leaving group tendency of these groups increasing in this order because the basicity is decreasing in this order. Naturally, acid chloride is most reactive. So the reactivity is increasing in this order because of the increasing leaving tendency of these groups. That is because of decreasing basicity of these groups. Clear? So that's about comparison of reactivity. Okay. Now we can quickly go through some reactions of acid chlorides. It is interesting that various acid derivatives can be prepared from the other. As I said earlier, if you go through the chemistry, it's interesting that one derivative change into the other during the reactions, most of the reactions. Of course, there are some special reactions also. We will consider the reactions of acid chlorides. Let me write generally, reactions in general, and we can explain the reactions, each one. These are various reagents for various reactions. Starting with, see, we have to be careful, you have to practice the reaction. What is the reaction with H2O called? Hydrolysis. It can be catalyzed by acid or base. Remember that. Acid or base. Actually, there is no need. This is quite reactive. See, this acid chloride will fume in moist air because it's highly reactive. You just open the bottle, it reacts. Because it is most reactive. Okay, what do you get? This is hydrolysis. And what is the product? You understand reactions in this way, as I said earlier. Whenever you go to a reaction, you see what is happening. So it is breaking like this. It is broken here. So what do you get the product? You get acid. So acid chloride is becoming carboxylic acid, the parent acid plus HCl. Then next is reaction with NH3 ammonia. What do you call this reaction? Breaking this bond using ammonia can be called ammonolysis. In general, we can call solvolysis like that. So if it is NH3, we can write like NH3 can be written like this. Okay. So what will be the product? You get amide here, another acid derivative, RCO, NH2 plus HCl. Okay. Coming to the next one, reaction with ROH and RNH2. It's interesting reaction. If you treat with ROH, alcohol, it will come like this. I can write RO and H here. Always see HCl is the byproduct. So what you get? RO will be attaching here and it is now ester. See, another derivative. Ester plus HCl. This reaction can also be called, actually this is known as alcoholysis. Hydrolysis, ammonolysis, alcoholysis. This can also be called acylation. Acylation. Why? Because on alcohol we are replacing this H by this group. What is this group? Acyl. RCO is generally called acyl group. See, acyl. If R is CH3, it is specifically called what? Acetyl, because it's come from acetic acid. Acetyl. This is generally called acyl. Acylation. Coming to the next reaction with RNH2, that means an amine. Here also there is a replaceable hydrogen. The reaction can be shown like this, like RNH here. So what is the product? H replaced by acyl group. So it is RCONHR. Okay, so N substituted amide you get. This is also acylation. Plus HCl. Always HCl is found with the byproduct. So to speed up the reaction, reactions are generally done more in basic medium. The base can neutralize HCl and remove from the reaction mixture, and reaction will be faster, or you get more product. Now next is reaction with carboxylic acid. If acid chloride is treated with carboxylic acid molecule, what about the reaction now? We can write it like this, RCOOH. It breaks like this. So what is the product now? Again another derivative, it is RCO, then this part OCOR. What is this? Anhydride plus HCl. Okay. So these are reactions. Now next one, what is this? LiAlH4, one of the popular reducing agent used in organic reactions. lithium aluminum hydride used for reduction, is a catalytic reduction. It is also shortly written sometimes as LAH, lithium aluminum hydride. So what is the reduction? What is the product? We can understand the reduction like this. Look at this. We are adding hydrogen. First you add 2 hydrogen atoms here to break this bond. It becomes aldehyde, but it will not stop at that stage. It will go to the next product. Just like carboxylic acid. So next is reducing this, breaking this bond, adding another H2 molecule. So what you get finally, it is now RCH2OH. You get primary alcohol. RCH2OH. You get primary alcohol. So these are various reactions. Now finally, we have 3 special reactions to mention. Name reactions, you can see, which are also related to these reactions only. But we particularly mention these reactions. Okay. The first one is Rosenman reduction. What is its importance? Rosenman's reduction is reduction of acid chloride using palladium barium sulfate catalyst. Palladium barium sulfate is a very special catalyst, right? Rosenman catalyst, and its reduction, of course, it is adding hydrogen in presence of this catalyst. What is the speciality here? This will give you aldehyde. So it differs from use of lithium aluminum hydride in that you stop at the aldehyde stage. It's a very important reaction. Okay, using this you get this further reduced into primary alcohol, but here it stops at aldehyde stage. It is because this catalyst is partially poisoned by quinoline, so that the further reduction is stopped. Okay, so if you have to convert a carboxylic acid into aldehyde, the route is first you convert carboxylic acid into acid chloride, and then you go for Rosenman reduction. The next is Friedel-Crafts acylation. This is a familiar reaction to you. Acylation, that you learn in aromatic hydrocarbons, where you discuss electrophilic ring substitution reactions or aromatic substitution reactions. So if you take this acid chloride and you treat with benzene, for example, any aromatic system, and you need a catalyst. What is that catalyst? Friedel-Crafts catalyst, and hydrous aluminum chloride. That is the most popular Friedel-Crafts catalyst. What happens? This acyl group get substituted on the ring, benzene ring. It is an electrophilic aromatic substitution. Okay, so you get the product, that is, you get acyl substituted benzene, COR. Okay, this is, and plus HCl. So this is what is called Friedel-Crafts acylation. And finally, Schotten-Bowman reaction. This is a special case of acylation reaction. Here you have to use not aliphatic acid chloride. The difference here is you are using an aromatic acid chloride. For example, you are taking benzoyl chloride, COCl. See, in naming acid chloride, the IUPAC method is, instead of oic acid, you replace this by oil chloride. That is the method, IUPAC method. So benzoic acid is named here benzoyl chloride. Ethanoic acid will be ethanol chloride. But the common name will be acetic acid, will be acetyl chloride. It will be YL, acetyl. Here there is OYL, that's the difference. So it is benzoyl chloride. It is treated with aniline. Okay. So the reaction here is this acidic or replaceable hydrogen. Hydrogen is replaced by this benzoyl group. That's the thing. And you have to use some base like NaOH or pyridine. See, Pyridine is also used as base in Schoenberg reaction. So in presence of some base like this, aniline, similarly you can take phenol also for this reaction. So the point is this, replaceable hydrogen on OH group, NH2 group are replaced by benzoyl group. That's very important. It is not acetyl group, benzoyl group in presence of base. So you get the product, that means here H is replaced by this group, so it will be NHCOPH. PH means benzene ring. Okay, so you get this kind of this is a kind of anilide, a kind of amide you get. Here also you have the byproduct, that is HCl. HCl is always a byproduct, a fuming byproduct in the reactions of all acid chlorides. That's all for now. Thank you.